In this video, we will estimate viscosity using the Stokes-Einstein relation from a diffusion coefficient measured by a DOSY spectrum in nuclear magnetic resonance, and compare the result with viscometer data. Along the way, we will build chemical intuition, write the math, analyze uncertainty statistically, and visualize the results with clear diagrams and graphs. First, the workflow. We measure diffusion with DOSY nuclear magnetic resonance, giving the diffusion coefficient, d, combined with a hydrodynamic radius, r sub h, at a fixed temperature, T. We apply the Stokes-Einstein equation to estimate viscosity, ETA. Then we compare the estimate with a viscometer measurement and interpret any differences. The Stokes-Einstein relation links diffusion and viscosity. It reads, d equals k sub b times t divided by 6 pi times eta times r sub h. Here, d is diffusion coefficient, k sub b is Boltzmann constant, t is absolute temperature, eta is viscosity, and r sub h is hydrodynamic radius that captures size and shape and boundary condition effects. Let us solve for viscosity. Rearranging gives eta equals k sub b times t divided by 6 pi times r sub h times d. We will use a temperature of 298 Kelvin, a Boltzmann constant of 1.380649 times 10 to the minus 23 joules per Kelvin, a hydrodynamic radius of 0.25 nanometers, and a diffusion coefficient from a DOSY spectrum of 1.00 times 10 to the minus 9 square meters per second. Let us substitute the values and compute. We will also compare with a viscometer value of 0.90 millipascal seconds. Here is a simple side-by-side comparison of the viscometer value and the Stokes-Einstein estimate, both in millipascal seconds. To see performance across several samples, here is a scatter of estimated viscosity versus viscometer viscosity. The dashed line is the perfect agreement line, y equals x. Then we compute statistics, bias in millipascal seconds, root mean square error, and r squared as a measure of agreement. Residuals, the estimate minus the measurement, help us see systematic patterns. Positive bars mean overestimation, negative bars mean underestimation. Now, uncertainty from the equation for viscosity equal k sub bt over 6 pi r sub hd, the relative uncertainty in ETA, assuming independent errors, is the square root of the sum of squares of the relative uncertainties of temperature, hydrodynamic radius, and diffusion. For example, if sigma t over t is 0.3%, sigma r sub h over r sub h is 10%, and sigma d over d is 5%, then sigma eta over eta is roughly 11.2%. This means a 10% uncertainty in size dominates the error budget. Why do deviations occur between the Stokes-Einstein estimate and viscometer measurements? 1. The solute may not be spherical, for example a rod or disk, changing hydrodynamic drag relative to a sphere. 2. Boundary condition may be slip versus stick at the interface, modifying the 6 pi factor. 3. Finite concentration introduces hydrodynamic interactions and changes in effective viscosity. For temperature miscalibration or drift in DOSY or viscometer. 5. Convection or probe artifacts in diffusion measurements. 6. Microheterogeneity of solvent, for example hydrogen bonding networks, creating location-dependent viscosity. 7. Model error for our sub-H estimation. These are common, and the statistics we computed help flag whether deviations are random or systematic. Summary: the Stokes-Einstein relation turns diffusion into viscosity when size and temperature are known. For our example, the estimate was within a few percent of the viscometer. Across multiple samples, we quantified bias, root mean square error, and r squared. Interpreting deviations requires both chemical insight about molecular shape and interactions and statistical tools to separate noise from bias.